Okay, so chapter 14, section 2 is talking about properties of carboxylic acid. So we'll talk about two things in particular. One is solubility, and then the other one is actually the acidity of the carboxylic acid and the acid-base reactions that occur. So first, carboxylic acids are one of the most polar organic groups. Organic functional groups. And this is because there's a lot of hydrogen bonds. So if you see in this interaction picture here, each lone pair on each oxygen can have two hydrogen bonds, and then the hydrogen of the alcohol can also have a hydrogen bond. So it's kind of like putting a ketone right next to an alcohol. So you have 5 hydrogen bonds all concentrated in one area. So it pretty much makes these molecules more soluble, or the most soluble compounds that we have in terms of types of functional groups. So this makes it so that if you have 4 or less carbons, you have a soluble compound. Or if you have 5 or more, you have a slightly soluble compound. So because you have such a polar group on there, you're pretty much going to be at least slightly soluble all the time, but it's not going to be 100% rule. For this class, that is the rules we're going by though. So then continuing on with the acidity of carboxylic acids. So carboxylic acids can undergo acid-base reactions. So what that means is that there's a proton that's shuttled back and forth to whatever is most basic, or whatever is most basic wants to have that proton. So as we've talked about, the carboxylic acids are weak acids, and so they can be deprotonated easily in order to form what's called a carboxylate ion. I can't talk tonight, guys. That is okay. So for example, if you put just acetate in water, you'll get an equilibrium with its carboxylate ion mixed with the water with an extra proton, which looks like this. So we have, I'm going to move that over just so it's not mixed in. There we go. Okay, so this is called hydronium. When you have a water atom that has an extra proton on it, it is positively charged. It's called hydronium. So in this case, the ionization of water, it's a pretty good equilibrium in general. But in general, it really favors having the hydrogen on the carboxylic acid. But it can happen, and there's a mix of it in solution. So the KEQ is 10 to the negative 7th. So that's why my equilibrium arrows are favoring the carboxylic acid, not the carboxylate ion. I'm going to just that's the carboxylate ion. In order to make this a more favorable process, what you can do is put it in base. And so if you add something like sodium hydroxide, so that's like water, but without a proton, right? You're taking one proton away and you're making it hydroxide, which is basic. That will drive the equilibrium towards the product. So you will make a carboxylate salt out of that. What that means is we're going to have that same ion, but now it will have a counter ion associated with it. So you see how I have sodium here in the base. So now I have a sodium carboxylate salt. And then in addition to this, I'll have water. So you can see where that hydrogen went. Sodium hydroxide stole a hydrogen from the carboxylic acid. So this hydrogen here was not on the base to start with, but it stole it from the carboxylic acid here. And then additionally, we will need to know how to name these carboxylate salts. And so the name of this particular carboxylate salt, you're going to put the name of whatever counter ion atom you have at the beginning. So sodium is the first word. And then you're going to have the same name as your carboxylic acid starting material, but you're going to replace the IC acid with ATE. So in this case, we started with acetate, which was our common name. I'm sorry, not acetate, acetic acid. And that made us form sodium acetate. So we're forming the same root word, and we're just putting ATE at the end instead of IC acid. And the sodium at the beginning is just to show what your counter ion is. And then because we're starting with a base, so we're adding an acid and a base, those like reacting really fast. So this is going to drive it towards the product. So now we have a KEQ of 10 to the 11th. So it's even stronger interaction and it's going towards your products now. So carboxylate salts, I am so sorry guys, my words are not coming tonight. Carboxylate salts, some uses of these in real life. So benzoic acid, when you mix it with a base, makes sodium benzoate here, and water. But the sodium benzoate is a preservative that inhibits microbe growth. So it's a preservative you'll see in a lot of like foods on the shelves and stuff like that. It'll have some sodium benzoate in it. And then something that you guys probably have heard of through the grapevine of your nutrition classes and everything like that, something called monosodium glutamate. So this molecule here, if it's protonated, it's just called monoglutamate. I'm sorry, it's just called glutamate. But then if you deprotonate just one side of the dicarboxylic acid, so you have one carboxylic acid here, one carboxylic acid here, make one carboxylate salt, and that's called monosodium glutamate, or it's the acronym that a lot of people know it for is MSG. So MSGs have been banned a lot in foods and have been shown to, or have been thought to have caused a lot of sickness in people. So that's what MSG, it's a preservative that gets put in food as well. So let's do a couple quick practice predicting the products of these equations. So write a balanced equation for the ionization of the following carboxylic acids in water and name the products. So there we go. So if we mix a carboxylic acid, acetate, with water, we're going to get our carboxylate ion and H3O+. That's going to be our product. So we're just shuttling one hydrogen over to water, and we get a negative charge on that oxygen because we're taking away a proton, we're taking away a hydrogen. Okay, so another example of this, we can do the same thing with this carboxylic acid now. We're going to draw the same carboxylic acid, now with a negative charge, and then plus H3O+. And that's all you have to do to show the ionization in water. And then we have some examples where we do the same thing, but now we're reacting with the base. So we're going to have a bit different products involved with this. So really what happens are we just swap places. So the potassium here, so I used sodium in the examples before. We can also use potassium or any other counter ion. They're going to just switch places is the easiest way to think about this. The potassium is going to swap places with the hydrogen of the carboxylic acid. So we have our acetate that has our potassium ion next to it. Plus we have water because we had that H swap places. And then we have the same thing. We'll draw our same carboxylic acid minus the hydrogen. add our potassium ion here to counterbalance it, plus water. I missed a step in these, as particularly in this last slide. It says name the products, and I didn't do so. So let's do it. Okay, so this first one, so we had our acetic acid. So we changed that to an 8 at the end. So this is just an acetate ion. We don't have a counter ion here because it doesn't have that sodium, potassium, lithium type thing there. So this is just called acetate. In this second example, we don't necessarily have to start from the carboxylic acid. We can just name the carboxylate ion if we wanted to. So we have 1, 2, 3, 4 butyrate is going to be my base, and then at the 2 position I have a chloro. So 2-chlorobutyrate. Just for good measure, let's go back to this last slide and let's name these as well. I know it doesn't say to, but let's go ahead and do it. So we have the same acetate, but now we have a potassium ion with it. So its full name would be potassium acetate. And then we have our cyclohexyl carboxylic acid. So cyclopentyl, 2-cyclopentyl, nope, not 2-cyclopentyl, potassium cyclopentyl 8. Yep, because that would be cyclopentanoic acid. Yep, okay. My brain is not here today, guys. So this carboxylic acid is cyclopent. So it would be cyclopentane, but now it's going to be cyclopentanoic acid. So the name of the carboxylate would be potassium cyclopentanoate, which is a mouthful. I will not lie. That is why it took me a moment. Yeah, so that's all of our practice. That's the rest of the material talking about carboxylic acids. And then we'll learn a little bit more in the next section, how to use carboxylic acids in a reaction to make esters. But I think that's all we have for this section. So I'll see you guys next time.